Okay, we'll begin, and I just want to check in with you guys, see how everyone's doing. Thursday will be our final exam, so today is our last lecture, and I hope you feel like you learned some stuff. Let's see. I want to talk a little bit about the final exam. I'm still writing it, still trying to figure out exactly how to go about testing some stuff. But let's see. Maybe I can just write, and maybe I'll make my text bigger. Okay, so I'll have some general questions. So let's just talk about final exam. All right, so it'll be handwritten here in class, normal lecture time. So, you know, about 1 hour, 50 minutes. Okay. So it'll probably open up with some general kind of conceptual questions, or I don't know, general questions. All right, so and then I just want you to answer with, you know, 1 or 2 sentences. Okay. I'd rather not read long paragraphs. Okay, so, you know, what is the point of Monte Carlo methods? And when would we use these methods? I think that's a fair question, right? All right, let's say if we want to learn the expected value of a distribution, how would we accomplish this using Monte Carlo methods? And you would just give a short 1 to 2 sentence answer. These notes will be posted online, so you know you don't have to seriously write this down. Okay. Maybe I'll ask, what is the difference? So, general conceptual questions, I'll say, you know, I'll select a few of these. Okay. What is the difference between Markov chain Monte Carlo and, quote, regular Monte Carlo methods? How do I... Okay. Maybe what makes the Metropolis algorithm and Metropolis Hastings algorithm particularly well suited for Bayesian models. Okay, what is it about these? Okay, and then maybe how does the Metropolis algorithm still find the appropriate region of interest even if you give it a terrible starting location, right? So I think we saw this in your homework. It took a little while. So you did the Gibbs Sampler and the Metropolis algorithm. And in both cases, we gave them terrible starting locations. The Gibbs Sampler found the appropriate region a little faster, but the Metropolis algorithm still found it, even after some wandering, but it still managed to find it. So, you know, what is it, I guess? What is it about the Metropolis algorithm that, I don't know, pushes the chain to the right location? Okay. So that, you know, those are some conceptual questions, and I'll select some of these. Okay. What else? Okay. And maybe I will make you do trying to figure this part out. Maybe I'll do perform some MCMC by hand. I know this is terrible. We don't want to do this, but you know, so for example, we might do Metropolis algorithm, and then I'll provide target distribution, and then I'll describe the proposal distribution, and then I'll provide some random numbers. So for example, maybe the proposal distribution will be a normal distribution centered at the current value with standard deviation equal to 5, okay? And then maybe I'll provide some numbers drawn from normal with mu equal to 0 and sigma equal to 1. Okay, and then so you would need to convert the standard normal values to proposal values, right? Okay, and then decide whether to accept or reject the proposed values. perform a couple iterations, a few iterations of the chain. Does that make sense? So I might, yeah. That's just an example. Gibbs Sampler is a little bit more complicated. I'm thinking of giving you a I will provide the target distribution as a target distribution. All right, so here, Gibbs Sampler. This is what I have in mind. The target distribution is a two-dimensional discrete distribution. Okay, and I will provide the target distribution as a two-way table with probabilities. So, for example, it'll be like x1, and then we'll have x2, and we'll have we'll say x1 equals 1, x1 equals 2, x1 equals 3, and then x2, it'll be x2 equals, I don't know, it doesn't matter, 7, x2 equals 8, and x2 equals 9. And then, I don't know, maybe I'll put 10%, 15, and 20%, and then maybe 15, 15, 5. Oops, I don't know what happened here. What did I say? And then, I don't know, I got to figure out some numbers here, but basically, and some more numbers, right? Maybe this will be 10% and 30. I can't add up. 30, 35, 65 plus 25 is 90. Okay, so I think this has to be like 2%. And 8%? I don't know. Do these add up to 100? 1.00 or something? Okay, so then maybe I will say perform Gibbs sampling. I'll say start with x1 equal to 1 and x2 equal to 7, and then perform Gibbs sampling and keep x1 constant for the first iteration. Okay, and then I will just provide a sequence of uniform values drawn from unif 0, 1. This one. Does that make sense? And can you guys do this? And so what you would need to do is you need to find the conditional distributions, right? Which is simple when you have the two-way table, okay? And obviously, if you have the two-way table, you can just sample from the two-dimensional distribution directly. But this will kind of at least force you, I think, in a simple way to create conditional distributions and then sample them accordingly, right? Okay, and then do a few iterations of that. And then maybe I'll have okay, and then how do I? Okay, and then a few more questions. So I was thinking probably just some conceptual questions regarding the Metropolis algorithm, used for the deciphering. Okay. So, you know, I don't want to, like, for example, I could ask something like, okay, so the Metropolis algorithm is used to, the point of the Metropolis algorithm is not to decipher code, and it's not an optimization code either, right? The Metropolis algorithm is not an algorithm for optimization. Okay, it is an algorithm to generate samples from a target distribution. Okay, but you know, for the deciphering, we use the Metropolis algorithm to give us a letter mapping with a high probability. Okay. Okay. So, you know, why would, you know, why is the Metropolis algorithm still successful? In helping us achieve this. Thinking of other questions. All right, yeah, okay, maybe an easier one. Okay, how many possible cipher mappings are there? And then how does using the Metropolis algorithm reduce the number of cipher mappings we need to check? I don't know. Maybe other questions. Covering. Okay, and I think that's fair for a final exam. We'll keep it something like that. Okay, are there any questions? So these are a little bit more, or a lot of these are a little bit more conceptual, and then yeah, you will have maybe some calculation stuff or some stuff to make you do the algorithms by hand, just to kind of make sure you got a handle on that. Yes.
Will the final covers and convert in the midterm? Just like the Monte Carlo integration or something?
No, I'm not going to be like directly covering stuff that was covered on the midterm, okay? But I mean, and loosely, like for example, doing the Metropolis algorithm by hand, if I provide numbers from the standard normal and you have to convert it to numbers from another thing, that's loose, that's related to stuff covered prior to the midterm, but that's fine. Or if I give you a sequence of u values drawn from uniform 0, 1, and you have to convert it into values drawn from some discrete distribution, that's technically covered from before the midterm, but I think it's fair, right? This is all, everything kind of builds off of each other a little bit. So, but am I going to ask questions that were already asked on the midterm? No, I'm not going to do that. Okay. All right. So this is my request. On Piazza, please don't just put these questions up and then answer. Like you can discuss concepts and you can discuss the topics, and if there's something you're confused about or you want to talk to each other about it, that's fine. But please don't just say like this question and this answer, right? Like I don't want it to just turn into like memorize what people wrote on Piazza or something. Okay, so I'll just write that. Discussion on Piazza is fine, but no just blatant question posting and answering, okay? Good. But please do not simply we'll say paste a question and await an answer. Paste a question here. From here. Okay. Anything else about the final? Yeah. Yeah.
Should we just go through like conceptually and answer them, or like explain to them like the thought process there?
So all right, let me try to see, right? Like, I guess I just don't want somebody to just take this question and write, so what is the difference between Markov chain Monte Carlo and regular Monte Carlo methods, and put that up on Piazza, and then people are like, oh, okay, the difference is this and this and this. I want it to be kind of, and I guess I just don't want Piazza to be abused, and I'll have to be the judge of that, right? Like, I suppose... Yeah, I mean, there's ways around this, right? Of course, like somebody could put one question and just says like, I don't know, what are regular Monte Carlo methods versus Markov chain Monte Carlo? I know, and like that's slightly different and stuff, but I guess, you know, a discussion of concepts and ideas from the class, I'm totally for. I just don't want it to turn into let's come up with a student version of an answer key, okay? And I guess I'll have to be the judge of like if this question is kind of pushing the boundaries or whatnot. You know, of course, I want you guys to study and learn from each other and help each other out. I guess I feel like I'm being generous in giving you kind of a partial question pool, and I guess I don't want to feel like that generosity is being abused, okay? And so I just don't want a straight, you know, student-created answer key on Piazza, okay? And then, you know, and likewise, you know, don't, yeah, I don't know, okay. All right, is it, I don't know if that helps, but that's kind of what I'm thinking here. Okay. Again, I hope you've enjoyed the course. I hope you found what we've covered interesting, and did the evaluation window close already? Okay, it's already closed. Okay, well, if you consider, so I hope you left evaluations, and if not, consider leaving one on either Bruin Walk or Rate My Professors. And then, and so for the rest of today's class, I want to kind of show an example of the Gibbs Sampler being used. Now, again, I'm not, and this is the risk, I'm not going to test you on this, but I think it's very good. And I think it's an interesting example that you can learn and benefit from, okay? So, at the risk, you know, please don't just get up and leave. So I think we left off on Thursday talking about hierarchical models, right? And we said in a hierarchical model, okay, the idea is there's a hierarchy, okay? You know, our data comes from a distribution with unknown parameters. And then the unknown parameters themselves are drawn from another distribution. Okay, with unknown, and we might call these hyperparameters. Okay, so for example, if we were talking baseball, okay, we might have a beta distribution with hyperparameters alpha and beta, okay, and this will generate theta sub I comes from the beta, okay? And each player has a different theta sub I representing batting average. Okay, and then from here, we'll generate a sequence of data which will go like 0, 0, 1, 1, 0, 1. Okay, and this is kind of a sequence of hit slash miss for each at bat. So did the baseball player get et cetera, et cetera, et cetera. So each player has their own theta that we don't know, and then we also see their sequence of data, their zeros and ones of getting hits or misses and things like that. Okay, and meanwhile the alpha and the beta come from some, we will maybe just have an uninformative prior. Maybe we'll call this a hyperprior, uninformative hyperprior. Okay, so that's the hierarchical model. And how would Gibbs sampling work for this? Okay. So to use Gibbs sampling here is, we want a we want to kind of factor this out into conditional distributions, right? So we have a joint distribution for all the parameters that need to be estimated. Okay. Need to be estimated, I guess, based on the data. And so we would have the distribution of theta 1, theta 2, theta 3, up to theta n, and alpha and beta given our data y. And okay, so using Bayes' rule, this just becomes the distribution of theta 1, theta 2, theta 3, all the way up to theta n, alpha, beta, y, divided by the probability of y. This will just be proportional to the top part, which can then be factored into the likelihood times the prior, right? So we have the likelihood of the data given theta 1, theta 2, theta n, alpha, and beta times the prior of theta 1, theta 2, alpha, theta n, alpha, and beta. Okay, And if we think about it, each y only depends on theta, right? And technically, it's just if we subset, like, I don't know, our data, y sub I only depends on theta sub I, right? So this becomes probability of basically, if you think of y as a matrix, so this will be, I'll do y1 based on theta 1 and y2 based on theta 2 dot 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 up to probability of yn based on theta n. And then if we think about where theta comes from, each theta 1 comes from alpha beta, probability of theta 2 coming from alpha and beta, dot dot dot. So theta n given alpha and beta. And then lastly, the prior distribution of alpha and beta. Okay, so this is, this is the product of the likelihoods of each, I don't know, batting sequence given the player's batting average so this would be the, this is the probability of the, the yi given the theta I, dot dot dot. So that's the products of the likelihoods, and then multiplied by the product of the batting average being drawn from the prior distribution. Theta I coming from alpha and beta, okay? And then times the prior distribution of alpha and beta, okay? All right, is this okay? How I factored the joint distribution for all the parameters. So we have all the parameters in the giant model, right? You're like, I don't know, you maybe have batting records of 50 players or something. So then there's technically 50 theta values you need to estimate plus the alpha and the beta, okay? And then you just have the batting records for the 50 players. And so everybody is kind of thrown in here and we factor them out, okay? But in the factoring out, I don't know, it's not actually too bad, right? Because if we think about, this sequence of hits and misses, that's depends only on that one player's batting average, okay? We don't need to like try to relate it to other players' things. So we can factor this out. Once we make it conditional on player one's batting average, that will explain the hits and the misses. And so factoring out the conditional probabilities is not too complicated because each player's batting sequence depends only on that player's batting average, and it's not dependent on anything else, okay? And then if we think about, okay, what is the distribution for the player's batting average? That's the theta being drawn from a distribution depending on alpha and beta, okay? And so these parts are, because the hardest part in Gibbs sampling is figuring out the conditional distributions. And so this conditional distribution what is this? What is, how do we calculate the likelihood based on a batting average? What kind of probability distribution is used here? A Bernoulli, right? So this is just going to be, whoops. Bernoulli or binomial, if you're just going to use the end result, okay? And then what kind of distribution are the thetas being drawn from? This is drawn from a beta distribution, okay? Okay, and then the last part, figuring out the alpha and beta, this part's a little bit complicated, okay? So this one may be complicated. May be complicated, and the conditional distribution might not be easy. Okay, so and let me just go back. Okay, so to do the Gibbs sampling, so we'll use we'll use Gibbs sampling and then the Metropolis algorithm. So for each player, we will kind of we will update the conditional distribution. Okay, so we'll say, you know, for player J, given alpha, beta, and the data Y for player J, the conditional distribution, so this is will be drawn from a beta distribution, and we're going to take alpha and add up basically the k sub j's and beta plus the n sub j's minus k sub j. So kj would equal the sum of successes, and then nj would be the total length of the sequence. Okay. And and we covered this earlier on when we were just looking at the beta binomial model, right? So this is what we have, and we do this for we draw a new theta value for all the players in our data. Okay, so if there's 50 players, there's 52 parameters to estimate. We're technically in a probability distribution of dimension 52. Okay, and so a standard Metropolis algorithm would require you to propose all 52 values at the same time. Okay, and we can see how that could run into problems, because maybe 49 of those values that you propose are reasonable, good values, but if the remaining 3 values just have very low probabilities, then that whole set of 52 values is going to get rejected, right? And so by doing them one at a time, we just sample 1 out of the 52, and then we go down the line, okay? And so we draw a new theta value for all the players in our data, okay? And then lastly, we still need to draw a new alpha and new beta, okay? Because these are still parameters that we are also trying to estimate, okay? So we draw a new theta value for all the players in our data, okay? Okay, so yeah. And then, yeah, we draw a new theta value one at a time. Okay. All right, and then we also need to draw values for alpha and beta, okay? But finding the conditional distribution of alpha and beta is a little bit tricky, right? Alpha and beta, given all other parameter values, is tricky, okay? It's for the players, it's not too bad because each player's theta is independent of the other players, okay? Once you have the alpha and betas defined, there's not like this intermingling between each player's batting average, okay? So finding the conditional distributions of alpha and beta, that's tricky, and we want to estimate this, okay? And we can't just say like, okay, well, let's just ignore these or something. So what we're trying to do is we're trying to find the probability of alpha and beta given, I'm gonna just, instead of, I'm gonna write this to kind of represent all theta values, okay? And your data y. Maybe I'll make this a matrix, okay? So this is all theta values and then all data y. Okay. So just using kind of Bayes' rule, we got alpha, beta, theta, y. Divided by the probability of theta and y. But this, again, is just proportional to our y's given all of our theta values. And then probability of all the thetas given alpha and beta times the probability of alpha and beta, okay? So this is so the posterior distribution of alpha and beta is proportional to this, okay? So for this step, where we couldn't figure out the conditional distribution of alpha and beta, we can do a metropolis step, okay? We might have trouble. Okay, and then that just involves proposing a new alpha and beta and then accepting or rejecting it, right? So we might have trouble finding the conditional distribution of alpha and beta. We perform a metropolis step, okay? And then maybe we get possibly a new value for alpha and beta, okay? And then we repeat the process, which in our case is draw new values of theta j for every single player. Okay, and then, via Gibbs, and then draw new value of alpha and beta via Metropolis. Okay, and so what we've done is if we have 52 players, if we have 50 players, okay, we have 52 parameters in our posterior distribution, right? 50 theta j's plus alpha and beta, okay? So a regular old Metropolis algorithm would really struggle because it would require you to propose all 52 values at the same time, okay? And the probability that you successfully propose 52 good values is going to be very low, okay? But with Gibbs, we take this 52-dimensional thing and we split it up into 50 unidimensional things, right? We make them conditional and we just say, okay, theta j only depends on this and stuff like that. So we just make a bunch of conditional distributions that are much easier to sample from. And then the part where we couldn't figure out the conditional distribution, we say, okay, we'll do Metropolis for this part, okay? And a Metropolis of two dimensions is much more likely to be successful than a Metropolis of 52 dimensions. Okay, so we have 52 parameters in our posterior distribution. So Metropolis would attempt to propose all 52 at the same time. Attempt to propose all 52 values at the same time, which will lead to, very few proposals will be accepted. Okay. Instead, we use Gibbs, and this produces, we have 50 conditional distributions. Okay, one for each player. Okay, and then the remaining 2 will be done via Metropolis. So Metropolis is super great because you don't have to figure out the exact distribution. You just need to know that it's proportional to something, which lines up perfectly with Bayesian analysis. And then Gibbs is great because it reduces your complex problem of having a whole bunch of parameters down into a bunch of easy ones, easy conditional ones, okay? And the hierarchical model, Gibbs sampling is perfect for the hierarchical model because by understanding the relationship between the theta coming from its parent distribution, this conditional distribution relationship between the beta distribution up high and in each individual theta, that's a lot clearer and easier. We know that theta doesn't have dependencies upon the other thetas and stuff like that. So that conditional distribution relationship is clear, okay? Whereas, I know when I first introduced Gibbs sampling, I said, we had to do all of this math to figure out the conditional distributions. In a hierarchical model, the conditional distribution relationships are fairly clear and easy to go forward with, Does that kind of make sense? Okay, so I want to show you an example, and I'm really excited for this example. I know I only have like 50 minutes left in class time. So I hope I can do this, okay? So this is kind of so this is what I'll call an interesting hierarchical model example. I mean, the baseball one's not too bad, but yeah, here we're gonna have document classification. Okay, and the hope is, well, this is kind of related to sentiment analysis. I don't know if you're familiar with sentiment analysis. It's the idea of like somebody writes an article or maybe posts a tweet, and we want to know, are they saying something positive or something negative? Okay, and there's all sorts of different ways that you can go about this, but one is kind of this kind of bag of words model, and you just say like, okay, based on the words that appear in this message, can we say this is a positive message or is this a negative message, right? So if you see words like awesome, terrific, wow, great, likely a positive message, right? Okay, bag of words is not going to pick up on sarcasm, right? So if it says good job, Jeff, you're not going to know that that was maybe full of sarcasm and negative or something. But words like awful, terrible, sucks, these would be negative, okay? The data I'm going to use is like a very simplified thing, but basically the hope is to take documents and based on the words we see, we want to classify them. Okay? But we want to do this in an unsupervised method. We don't want to tell the computer these are positive sounding words and these are negative sounding words, or that these words associated with this type of document. Here we're just going to use a two-class document classification system, okay? We don't want to say these are the words that make it like this, put it in this category, and these are the words that put it in this category. We want it to say, just look at all the words and see if you can perform some classification and put them into two clusters. Okay, so we don't want to have to tell them these words are good and these words are bad. Okay, so we want to do it in an unsupervised manner. Okay, we do not want to have to say these words are associated with class A, and these are associated with class B. We want the computer to figure this out on its own. Okay, so let me pull up. I've already written some code here to do it, and so we're gonna do we're gonna keep this easy, okay? Okay, so what I have is I've got the text from two children's books. One is Green Eggs and Ham, and the other is Go Dog Go. Okay, and I don't know if you guys know these, like, they're great books. Okay, so So green eggs and ham is like Dr. Seuss's book, and Go Dog Go is, yeah, here we'll look it up. Green eggs and ham. I don't know. All right, my internet's not running. Okay, but let me just show you the words. And this is just made to be as simple as possible. And I have it as homework 6, but I think, all right. So green eggs and ham, it goes, I am Sam, Sam I am, and then character 2 goes, that Sam I am, I do not like that Sam I am, okay? And it says, do you like green eggs and ham? And then there's all these things, and it goes on, and Sam is trying to get the character to eat the green eggs and ham, and he says, will you like them in a box? Will you like them with a fox, you know? Or yeah, would you like them in a house? Would you like them with a mouse? And then he says, I do not like them in a house. I do not like them with a mouse. I do not like them here or there. I do not like them anywhere. I do not like green eggs and ham. Okay, so anyway, I took the text of green eggs and ham and I chopped it up into 10 pieces, okay? And then over here, I took the text of Go Dog Go, all right? And Go Dog Go is just another kid's book, and this is how the sentence in Go Dog Go goes. It starts off, the first sentence is dog, and there's a picture of a dog, and then it goes, big dog, little dog, big dogs and little dogs, black and white dogs. Hello, hello, do you like my hat? I do not. Goodbye, goodbye. And then there's more pictures. One little dog going in, 3 big dogs going out. And this is just like the entire text of a book, right? The sun is up, the sun is yellow, the yellow sun is over the house. Now it is night. 3 dogs at a party on a boat at night. Dogs at work. Work, dogs, work. Okay? And these are the things, and I took the text of Go Dog Go and I chopped it up into 9 pieces. Okay? And so each of these pieces belong to either Go Dog Go or green eggs and ham, right? And so now, just imagine, I'm gonna cut these up, so now I have 19 little, maybe I print this out and I cut them up into pieces, and now you have 19 little pieces. 9 of them belong to Go Dog Go, 10 of them belong to green eggs and ham, and we just shuffle them together into a bag, and we dump them out, and I give you the task, and I say, okay, put these into 2 categories. And it would be very easy for you as a human if I say, here's a sentence, right? I do not like them in a box. I do not like them with a fox. I will not eat them in a house. And I say, okay, which book did this sentence come from? You'd say, okay, that came from green eggs and ham, right? And then, you come across something else, and then, and it says, a green dog over a tree, a yellow dog under a tree, 2 dogs on a house and a boat in the water, right? And I say, which book did that come from? And you'd say, that came from Go Dog Go. Because you are people and you are smart and you can figure this out, right? The question is, can we get the computer to do the same thing? And we're not going to tell it, look for dog books, look for books about green eggs and ham. Just look at the patterns of the words and sort them accordingly. Okay, that's what we want to do. All right. Okay, so the first part of this code, before I get into the model that we're going to build up to accomplish this, the first part of this code, and there's a fair amount of it, is just turning our text into something the computer can read. Okay, and so we're going to take this. I have green eggs and ham. So corpus is just the text. Okay, and so here we've got 19, it's a character vector of 19, and each entry is just one of these things, right? Right, hello again, hello, do you like my hat? I do not like that hat, goodbye. There's like a story there, okay. I'm gonna use this code called text mining and snowball seed. These are different libraries that offer this thing that create corpuses, okay? okay? And so what a corpus does, okay, is that it will do things like stem the words, okay? So let me just show you the original text that I read in. Oops. Started off with, I am Sam, Sam I am, that Sam I am. I do not like that Sam I am, okay? If I, after I run it through this text stuff, just to kind of make it a little easier, it removes what's called stop words. Stop words are words that are like super common in English that will not add significant value to the text analysis. Words like is and that and the and a, these are all removed because these are too common for us to say, oh, because we saw the word the 50 times, it's got to be this kind of document. So it gets rid of all of those things. So green eggs and ham, which relies on a lot of repetition for like this pattern, you know, rhythmic reading, just becomes Sam, like green eggs, ham, right? And then if we look at the like an example from the dog book, so let me just go to like, so here's well, maybe, okay, so here's another one. So I will eat them in a box, I will eat them with a fox. If I after we remove the stop words and do the stem aim and things, it will be will eat box, will eat fox type of thing like that, okay? Let's just versus, so here's, you know, the sun is up, the sun is yellow, the yellow sun is over the house. It just becomes, you know, the sun is up gets reduced to sun, okay? That's like the only word that's of significance in the sentence here. So we get sun, sun, yellow, yellow, sun, house, hot sun, hot house, right? Word stems reduce house, houses, housing, house, I don't know. Are there other forms of the word house? They all just get reduced to H-O-U-S, okay? Things like that, okay? Party gets reduced to, so this is like partying, parties, party, they get reduced, okay? So these are just things that you generally perform to the words to kind of clean them up so that you know, your word model doesn't get distracted, okay? Then we create something called a document term matrix. So this will just take all of these things that say sun, sun, yellow, yellow, sun, house, and instead of leaving it in that form, it's going to create a tally of the word, okay? So, so for example, if we look at document 1, and we look at the words that appear in document 1, the word anywhere appears once, the word egg appears 3 times, green appears 3 times, ham appears 3 times, like appears 9 times, and Sam appears 8 times, okay? And then we can just kind of verify that and see, you know, if we ask, you know, how often do green eggs, does the word green appear? It does appear indeed 3 times and stuff like that, okay? So the document term matrix just shows each word and its frequency, and it does this for all 19 documents, okay? All right, is that okay? And then we can create this, do word counts, and so this, I'm just kind of showing the full thing, and so you can see, you know, how often each of these words appear, right? Okay, and so for example, you know, in go dog go, the word egg doesn't appear any times, okay? But the word green does appear, and you know, the word house appears in go dog go and stuff like that, okay? All right, is that okay? So if I ask, the dimensions of this thing, here we've identified 59 unique words, that were not stop words, and a total of 19 documents, okay? And this is just like a simple toy set, right? We can obviously expand this to something a little bit more complicated. Okay, so the way we are going to do this is we're going to just say, all right, let's think of how the documents are generated, okay? So we're going to create our document generating model. Okay, so first off, we're going to have the document is going to come from class A or class B, okay? And so the label of the document L sub j will come from a Bernoulli model with parameter pi, okay? So Lj equal to 0, maybe this is the document comes from green eggs and ham, okay, or is, class A, and then we have Lj equal to 1 is doc is go dog go, or class B. And so we're going to just say which class the document comes from is L sub j, and that's going to be drawn from a Bernoulli model, and so pi will just be the probability, the parameter for the Bernoulli, which is going to be just the probability of, class A. Okay. So the label of document is just a Bernoulli. Is that okay? And then we will have two word probability vectors, okay? And so technically, so we have, we will have a word probability vector theta for each class, okay? So we have theta Lj is the word probability vector for the document which has class Lj. So for example, theta 0 is a vector of probabilities for, I guess, all the words technically in the English language, for documents in green eggs and ham. Okay, and so what this will be is is, let's say there are, let's pretend, I don't how many words there are in English, okay? But let's pretend there are 50,000 words that are non-stop words, okay? Pretend there are 50,000 words, okay? So theta 0 is of length 50,000, and the sum is equal to 1, okay? Now technically, after we analyzed the corpus, there were a total of 59 unique words total in the entire document corpus, right? So technically, so our theta 0 only has to be of length 59, okay? But, okay, so I'll say in our document corpus, there were only 59 unique words. So theta 0 is length 59. Okay? And what we have is theta 0, words like theta 0 green, if we could kind of parse it this way, would have, you know, high probability. Theta 0, not eggs, would also have a high probability. Sam would be high, okay, high probability. Whereas the word dog does not appear. This will have a low probability, okay? So these are the vector of probabilities associated with words that are being generated for green eggs and ham, okay? So green and Sam appear often in docs of class 0, okay? The word dog is rare for docs of class 0, okay? And then, so you have theta 0, and then meanwhile you also have theta 1. Dog will have a high probability. And theta 1 egg will have low probability, right? So dog is a common word for docs of class 1. And egg is a rare word for docs of class 1. Okay? Is that okay? So we have two theta parameters. We have two theta vectors, a theta 0 for documents coming from class 0, and we have theta 1 for documents coming from class 1, okay? And each theta is kind of a vector, I guess of length 59 in our case, showing the probability of each word, of each of these 59 words. So if you have a document of class 0, words like green, egg, and ham will appear with high probability, and words like dog will appear with low probability, okay? And just the opposite for the other thing, okay? But remember, you know, we know this because we know about these things. Again, we're trying to get the computer to estimate all of these things on its own, unsupervised, okay? So these are, this is what we have so far, okay? Is we pick the documents get generated, okay? And then the actual words are generated by a multinomial model, multinomial distribution. Okay, are you guys familiar with the multinomial distribution? So the binomial distribution will be, you say something like, I'm going to flip the coin 30 times. How many times do I get heads and how many times do I get tails? And a random draw from the binomial distribution will say, you got 14 heads and 16 tails. Okay, binomial distribution will produce a number of successes and a number of failures, a random draw from that. Okay, a multinomial distribution is something very similar, except you are, rather than just having two sides like a binomial, you can have multiple category outcomes. So it could be something like, I'm going to roll the dice, roll a single die 100 times. How many times did I get face 1? How many times did I get face 2? How many times did I get face 3? And then so if you say, oh, I rolled it 100 times, it'll say, you got 12 ones, 17 twos, 13 threes, and something like that. That would be a random draw from the multinomial, okay? And so here, now we are pretending we have a 59-sided die. Some of the sides have higher probabilities than other ones, and we draw, we generate a random document by rolling this multinomial die, okay? And it will say, okay, your random draw from the multinomial distribution produced a document with the word green 4 times and the word Sam 6 times and something like that, okay? So the actual words and their counts are from a multinomial distribution. So this will be a vector of word counts for document J. Okay, so this might be this, and this will come from a multinomial distribution. Which will be by the number of words in J and theta Lj. Probability vector for the document class. Okay. So, for example, you know, maybe we'll say, you know, multinomial 100 words, I don't know, maybe not 100, we'll say 60 words with theta 0, okay, which will have, you know, green 0.1 and egg as, you know, 0.08 ... dog has probability 0.000001, okay, something like that, okay, where and then the sum of the thetas, and so a random draw might produce the vector green appears 7 times, egg is 5 times, ... and dog appears 0 times. Okay, so kind of like we can see, you know, let's look at the document term matrix. So here's one document that we've generated, okay? And we see egg appears 3 times, green appears 3 times, ham appears 3 times, like appears 9 times, and then words like big, black, blue, dog, goodbye, these all appeared 0 times, okay? So we can treat each document as one of these things, whereas if we look at another document, okay, eggs in green and ham appear 0 times, and the word dog appears 5 times, the word sun appears 4 times, and things like that. Okay? And so just by looking at this document term matrix, we can kind of figure out that this must be coming from go dog go, right? So we're looking at, how often did these words appear versus these words, okay? And so we're going to treat the word counts as multinomial, okay? All right, and then okay, so let's do our prior distributions. So we're saying LJ comes from a Bernoulli distribution with pi, and pi will come from a beta distribution with parameters basically alpha and beta. All right. All right, I don't know, whatever. 0 and 1, okay. And then our WJs come from multinomial with parameters RJ and theta. And then theta, which is the kind of this will come from a Dirichlet distribution with gamma vector theta, okay? So a Dirichlet is basically the multidimensional expansion of beta. So, a beta distribution has parameters alpha and beta and generate values between 0 and 1, which correspond to the probability of, getting heads on a coin or something like that, okay? A Dirichlet distribution, okay? This is our theta vector, right? So this is technically, you can think of it, and it's not exactly this because they're not all independent, but you can think of this as if we break down theta into theta 0 would come from some distribution between 0 and 1. Theta, I'm sorry, I should say theta 0, 1 and theta 0, 2, theta 0, 3. And each of these are coming from different, they're like beta distributions, but for every single word, right? And this goes on to theta 0, 59, because if we have 59 words, each of those words has a probability associated with it, and that probability has to be between 0 and 1, okay? Where it's more likely closer to 0, because there's 59 of them, okay? So a Dirichlet distribution has a bunch of these things, and it's the multi-dimensional or multi-categorical version of the beta distribution. So the beta distribution is a distribution of probabilities, and the Dirichlet distribution is also a distribution of probabilities, but for a bunch of categories, okay? So the draw from this Dirichlet distribution will produce a vector of 59 values. All of them will add up to 1, and each one represents the probability of each of those 59 words, okay? And so, the beta distribution has 2 shape parameters. The Dirichlet distribution will have 59 shape parameters because, I don't know, they're kind of like counts, sort of. So this, the kind of the parameter vector of 59, okay? All right, and then we have, okay, so let me just kind of draw the picture, our hierarchical model picture. Okay, so this is the the parameters for the Dirichlet distribution that will produce the word vector probabilities. Okay, so this is the Dirichlet distribution. This will generate. Oh, I'm so sorry. Not the Dirichlet. This needs to be. Okay, parameters for the Dirichlet distribution that will produce the word vector probability. Let me just extend this over to here. Okay, and so this will produce our vector theta. Okay, and we have two of these. Okay, so we have a theta 0 and a theta 1. Okay, so we've got these some kind of prior parameter Dirichlet distribution, and this is going to produce this. Okay. Meanwhile, you've got shape parameters alpha and beta. These are the parameters for the beta distribution. That will produce pi. Okay, so here we have a beta, and over here we have a Dirichlet. Okay, and so this produces the parameter pi, and from there you have a Bernoulli that produces the document label LJ. Let me create a plate. This is for each of the n documents. Okay, and based on the document label and the theta vector here, we will produce a series of words, okay? Okay, and so this will be, you have RJ words in the document. And then each word is determined by kind of the multinomial. So it's a multinomial thing. So this is what we have. Our data is the word counts, and based on that, we want to infer back or get Bayesian estimates for what these theta vectors are and stuff like that. Okay? So that we can figure out the document label. This is what we want. We really just want to know what's the document label. Is that okay? So it's like you flip a coin, because if we're like we know this is not how documents are generated, but we're pretending that we have this model where we flip a coin and we say, okay, are we going to talk about eggs or are we going to talk about dogs? Okay, we flip a coin and then we say, oh, it landed heads, so we're going to be talking about eggs. Okay, if we're going to be talking about eggs, what are the words that I would be using? And we look at our probability vector of words and it says, okay, well, you want to make sure you want to talk, if you're going to talk about eggs, you should talk about ham and you should talk about green and foxes and boxes and I don't know, whatever else appears in that book, okay? On the other hand, if we flip tails, we would say, okay, we're going to talk about dogs, and if you talk about dogs, then talk about, I don't know, house and party and car and whatever, okay? Okay, so the we are going to kind of factor all of this out, and okay, so the joint distribution of everything. We're going to run out of time. Okay, well, all right, so this is going to be the probability of, here we have something called a corpus. This is corpus of all documents, okay? We have a vector of labels. And then we have the parameter pi, your vector theta 0, your vector theta 1, okay? Given the parameters alpha, beta, and the gamma vector for theta. Okay, and then we're going to kind of factor or decompose into so these are our conditional distributions. Pi depends on alpha and beta, okay? The labels are drawn from the beta distribution, right? Or Bernoulli. Bernoulli, this is beta distribution. Okay, we have theta 0 vector depends on this gamma theta. This is a Dirichlet. Okay, we just say, you know, what depends on what? This is basically what we're trying to do. So these are corpus of class 1. So the words that appear in the corpus of class 1 depend only on, class 0, depend on the vector theta 0 and which ones are labeled as such. This is multinomial. And then I'm going to fit some more over here. So we have a bunch of conditional distributions, okay? So we're able to kind of take our joint distribution of everything and factor them down into conditional distributions. Okay, and then, so the next part, running out of time, but basically what we want to do is we want to say, okay, now that we have this, let's sample a parameter. We're going to do Gibbs sampling, right? So what you do is you sample a parameter and then you update that value in the next thing that you sample, okay? So we're going to sample a pi based on alpha and beta, okay? Once we have that pi, then we will draw new values of the Bernoulli, the L, and there's 19 of these L's to draw. And once we have that, that will come in over here. Over here we have a gamma theta that determines our Dirichlet, and we'll draw this vector theta 0, 59 values describing the word probabilities. And then and we draw this over here for a different one. And then we say, okay, now that I have new values for theta 0 and values for L, let's draw the probabilities of these word things, okay? And likewise, back in, when we did the beta binomial model for things like the baseball and whatever, the posterior distribution, you would take kind of the number of successes and failures and you would add those in to the alpha and the beta values in the prior distribution, right? So if your prior distribution was alpha is 5 and beta is 5, and then you had 10 successes and 2 failures, your posterior distribution would have alpha equal to 5 plus 10, 15, and your beta equal to 5 plus 2, 7, and your posterior would be 15, 7, or something like that. And we do something similar here, except we do a Dirichlet case, okay? So let me just kind of show all of this. MCMC Pack gives us the Dirichlet distribution and allows us to draw random values, okay? So here, this is, you can kind of see the hierarchy that we have, okay? I call this gamma pi 0 and gamma pi 1, but this is basically alpha and beta. So draw a random value from the beta distribution, and this will be pi. And then the labels L are Bernoulli, which is R doesn't have a Bernoulli. You have to use R binomial with size equal 1. So we're going to draw the random values for the Bernoulli from here. And then theta 0 comes from the Dirichlet thing, which in our case is based on just gamma theta. Gamma theta is the prior parameters, a vector of 59, and I just have 1 for everything. So this is your uniform, the equivalent of a uniform distribution in the beta, but for the Dirichlet. Okay, so right now, my random guesses for document labels is this. Okay, so this is just completely, this is my initial thing. Okay, and so for the Gibbs Sampler, what we do is we are going to say, all right, let's take the word count matrix and count up the total number of words that appear under these document labels. So if I just look at, word counts, well, we ran out of space here. But basically, I do this, okay? And so corpus 0W, this says, okay, so here, if we look at L, it says we're going to take document 2, document 4, 5, I'm sorry, L says document 1, 3, 8, 9, and 10, document 12, document 14, and document 17 belong to class 0. That's completely wrong. But this was just our initial random guess, right? Because it's an unsupervised model. We're not giving it any information, so we just say start with a random guess, okay? And our Markov chains say you could start off in a terrible location and eventually we'll get to the right place, okay? So we're starting off with a terrible location. We're saying document 1 and 3 belong to class 0 and the other ones don't, okay? Because the true answer is that the first 10 documents are of one class, and then the other 9 are of a different class, okay? Because I just fed them all in, but the computer doesn't know that, and so it just thinks that documents 1, 3, 8, and 9 belong to the same class, okay? And we say, okay, go ahead and add up all of the words that you see in those things, okay? And when it does that, it says, okay, for the words that are labeled class 0, I get the word egg 7 times and green 8 times and the word dog 20 times and things like that, okay? And then, and we have it do it for the other document class, okay? And it says, okay, in the other class, I get the word dog 38 times, and the word egg 4 times, and the word green 8 times, okay? Whereas if we had the correct labels in one word, in one document class, we'd probably have, 50 green and 50 eggs and 0 dogs. And in the other one, we would have dog appear like 60 times and the word egg appear like 0 times. Okay, maybe green will appear a few times. Oops. Okay. And so what we do is we're going to do a few iterations of the Gibbs sampler. Okay, and the code is not that complicated. Okay, all we do is we're going to just say, okay, add up how many documents are labeled labeled document 1 or document 0, okay? And then take the current word counts, okay? And subtract out we're going to say, let's look at document 1, okay? Let's look at document 1, and what we're going to do is we're going to remove the word counts from document 1 from these corpuses, okay? So if we look at word counts for document 1, this is the one where it says lots of green eggs and ham. What we're going to do is we're going to say, let's subtract these out from our corpus, okay? And then let's update the values that we're going to use for drawing our random beta distribution and our random Dirichlet, okay? And so we just kind of fix up the Dirichlet things, okay? So we're just basically doing conditional distributions for each of these, all right? And so so we run through that, and again, the computer has no idea what's going on. It's just saying, okay, we're going to update the counts accordingly, okay? And it does that. And so this is, let me just expand this to be wide. Okay, so at the first iteration, it had terrible guesses, right? It said document 1 and 3 and 8 and 9 are class 0, and document 2, 4, 5, 6, and 7 are class 1, okay? After the next iteration, it shifted a few things around. It's just doing another random draw, okay? But it's shifted the conditional distributions around. And then it says, okay, we're getting different labels here, okay? So this is the second results of the second iteration, okay? And what you can see is that by around the 6th iteration, it's starting to get this a little bit close, right? By the 6th iteration, it's saying that the first 10 documents belong to the same class, but it's also guessing that the 14th document belongs to the same class as everyone else, and then pretty much all of these other ones belong to class 0. And then, by around the 10th iteration, and it goes so quickly because it's like a toy data set with very obvious answers. By the 9th, 10th iteration, it has correctly labeled that the first 10 documents belong to one class, and then the other 9 documents belong to the other class, okay? And we didn't tell the computer look for words like dog or green or things like that, but based on the words that appeared and using our conditional distribution in Gibbs sampling, it was able to kind of sort these out here. Okay, we'll end here. I hope that was kind of neat, and we'll see you guys on Thursday for the final. So good luck.